going to be T35 for design of reinforced concrete element. We are now moving on to look at the unit 4 of our course, and under this unit you are going to look at the design of reinforced concrete columns. To do that, as we did for the other course, we will set ourselves another question, and our question states to design and detail the concrete column at the intersection of the grid lines 7 and C using the limit states method as outlined in the BS 8110 part 1. For the procedure of our column design, we'll start by doing our preliminary sizing. We'll estimate for our load, analyze our columns for axial forces and moments, design for reinforcement, design for shear, check for deflection, cracking, and ultimately we do our detailing for our column. Now, revisiting our floor slab once again, the column we are designing for, or the column we are supposed to design for, has been highlighted by the red dot in the floor plan. Now, zooming again to our structural grid, we also identify the location of our columns, which is supposed to be at the intersection of our grid line 7 and our grid line C. Now, taking a section through our floor slab, we would realize that the height of our floor slab, or the height of our column from the surface of our ground floor slab to the topmost surface of our first floor slab is equals to 3,200. Now, moving on, we'll look at a section through our building. Now, looking at the section through the building, our room height, or our distance, or our height from the topmost part of our ground floor to the topmost part of our first floor, has a dimension of 3,000, and that is from the ground floor to our first floor. Then also, looking through the same section, we realize that the distance from the top part of our first floor slab to the topmost part of our roof beam also has a height of 3,000. So from our first floor slab to our roof beam, so then we would keep these parameters down and we'll call them as and when it is needed. Now, for our design data, again, we are designing for a mild exposure condition. The minimum grade of concrete that we are making use for in our column design is concrete grade C30. Our nominal cover for durability again is 25, and the same goes for the fire resistance. Our minimum dimension to our reinforced concrete is 200 millimeters. The grade of reinforcement is mild steel with a yield strength of 250 newtons per millimeter squared. The diameter of our reinforcement is 20 millimeters. Diameter of our links is 8 millimeters. Now, generally, columns can either be classified, or columns are either classified as short or slender. Now, a short column, generally, a column can either be classified as being short or slender. A column is considered to be slender when the ratio of the LEY over B and LEY over H is less than or equal to 15. That is in the case of a braced column, and the LEX over H and LEY over B is less than or equal to 10 in the braced column. On the contrary, when we have these ratios being greater than 15 in the case of the braced and greater than 10 in the case of the unbraced, the column is termed as a slender column. Now again, a column can also be termed as either being braced or unbraced. Now, for a braced column, it is said that a column is considered to be braced in a given plane if lateral stability of that structure as a whole is provided by walls, bracing or buttressing designed to resist lateral forces in that plan. Aside classifying our columns as either being short or slender, the columns can also be classified as being braced or unbraced. A column is considered braced in a given plane if lateral stability of the whole structure is provided by walls, bracing or buttressing, which are specifically designed to resist lateral forces within the plane which is being considered. Now, where no such element has been provided, or where no such element has been designed to resist lateral forces, then the plane, in that particular plane, then the columns within that plane is what's considered as being unbraced. Now, considering the type of building that we are designing for, or our residential building we are designing for, it can be seen that no such element has been designed within the building to resist lateral forces. So then our columns within the building can be termed as being what? As being unbraced. So for our design that we are going to do, we are aiming at designing for a column which is short and unbraced. We are looking at doing a design for a column which is short and unbraced, in which case our effective length in the x and the y direction divided by the depth of the column within that plane should be less than 10. Since we are aiming at doing an unbraced column design, that is short. To determine the effective length of the column, provisions has been made within the Bscode. The effective length of a column LE is given as beta LO, where the beta values are given in tables within the Deisgn. If we go to our Bscode, particularly the table number 3.19 and the table number 3.20, it gives various values for our beta for both the unbraced and the braced column. Now, because we are dealing with an unbraced column, we would focus our attention on the table 3.20, which gives the values of beta for the unbraced column. Now, if you pick any column, it has two end conditions. That is the condition at the top of the column and the condition at the bottom of the column. Now, within the structure that we are designing for, it has two different levels. It has the ground floor level and the first floor level. So that in deciding on the effective length of our column, we need to decide on the effective length for the first floor level as well as the ground floor level separately. So then, starting with our first floor level, we zoom into our table 3.20, which gives, as I said before, gives the values for our beta for the unbraced column. Now, the conditions at the various points of our column, i.e. the top part of the column or the bottom of the column, is being stated below the table 3.20, and it reads, for condition 1, it says the end of the column is connected monolithically to beams on either side, meaning that the column and the beam are connected as one element. They are not two disjointed elements which have been connected together, but then they are acting as one element put together. So then the end of the column is connected monolithically, or they are connected as one on either side, with the beam being at least as deep as the overall dimension of the beam in the plane being considered. Meaning that in the particular plane which is being considered, the depth of the beam has a minimum value equal to that of the dimension of the column. It therefore stands to reason that the depth of the beam can either be equal to the dimensions of the column or greater than the dimensions of the column. It moves on to say that where the column is connected to a foundation structure, it should be of a form specifically designed to carry moment. For the condition number 2, it says the end of the column is connected monolithically to a beam or slab on either side, which is shallower than the overall dimensions of the column in the plane being considered. The third condition states that the end of the column is connected to members which, while not specifically designed to provide restraints to rotation of the column, will nevertheless provide some nominal restraint. And the last one says the end of the column is unrestrained against both lateral movement and rotation. Example, the free end of a cantilever column in an unbraced structure. Now, if we take a look at the structure we are designing for, particularly our first floor structure. Now, given that the depth of our first floor beams and the depth of our roof beams are the same, in which case the depth of our floor beams, as we calculated for in the previous unit, was 400 millimeters. Then it means that at my first floor level, I have my beam depth being 400 millimeters, and I have my roof beam depth also being what? 400 millimeters. Now, if I have a case where my column dimension would not exceed the dimensions being given in my beam, which is the 400 millimeters, then I'm looking at the condition number 1, which states that my beam depth is equal to or greater than my column dimension. So then where I have my column dimension, not going to exceed the depth of my beam, then it means that at my end conditions, I'll be looking at condition number 1. Now, if I'm looking at condition number 1 at my end conditions for both the top and the bottom, since I have my beam at the top being 400 millimeters, the beam at the bottom being 400 millimeters, and me not looking at coming out with a column dimension of 400 and over, then it means that for my end condition at the top, at the bottom, I'm going to read within the first column, and within, or for my end condition at the top, I'll be reading what? Along my first row. Now, if I'm reading along the first column and the first row, then it means that my beta value for my first floor level column is going to be equal to what? 1.2. Now, initially, we identified the floor height of our building from the first floor to the top of our roof beam as being equals to what? As being equals to 3,000. Now, the LO of a column is given as the clear height between restraints. It is given as the clear height between restraints. So that it is going to be the distance from the top of the first floor beam to the soffit of the roof beam. Now, given that my first floor beam and my roof beam both have a dimension of 400, then it means that my clear space, my clear height between restraints is going to be equals to 3,000 minus 400, which would yield me a value of 2,600. Now, in finding my effective height between restraints, is going to be my beta multiplied by my LO. Given that my beta value is 1.2, it means that my effective length or my effective height is going to be equals to 1.2 multiplied by the 2,600, which gives me a value of 3,120 millimeters. Now, because I am designing for an unbraced short column, my LEX divided by H should be less than or equals to 10. Now, from inequalities, it means that my H value should be greater than or equal to my LEX divided by 10, where my LEX value is equals to what? 3120. Now, dividing the 3120 by 10 gives me a value of 312 millimeters. Now, this 312 millimeters can be approximated to what? 320 millimeters, in which case the height of my column within the X direction, or the depth of my column within the X direction, has a value of what? 320 millimeters. Now, if I move to my Y plane, my LEY over B should also be less than or equals to 10. Should also be less than or equal to 10. Now, again, by the same inequality, my B value should be what? Greater than my LEY over 10. In which case, I'm going to have it being equals to what? My 3120 divided by 10. That would also yield me a B value of 312, which can also be approximated to what? 320 millimeters. Meaning that if I pick my column at the first floor level, it has a dimension of 320 by 320 millimeters. Now, moving forward, I now come to the ground floor level. At my ground floor level, I have at the bottom of my column, the column being connected to a floor slab, and at the top being connected to what? My roof, my first floor beam. My first floor beam has, as we realized before, has a depth of 400 millimeters. Whereas when I come to my floor slab at the bottom, it has a depth of 150 millimeters. Meaning that at the bottom of my column, the restraining element, i.e. being my floor slab, is going to be smaller, or the depth of my restraining element is going to be smaller than what? The dimension of my column. And for that reason, we are going to make reference to what? Our condition number 2, which says that the end of the column is connected monolithically to beams or slabs on either side, which are shallower than the overall dimension of the column in the plane being considered. So that in the plane being considered, if I have it at the bottom part, my column being connected to a floor slab, then at my end condition at the bottom, I'll be looking at condition number 2. if I come to my end condition at the top, I'll again be looking at condition number 1. Why? Because I have a beam with a depth of 400 millimeters, and I don't anticipate that my column dimension would exceed 400 millimeters. So that if I have my beam dimension exceeding my column dimension, then it means that I'll be dealing with what? Condition number 1. So then for my end condition at the top, I'll be looking at condition number 1, in which case I'll have to read along the what? The first row for my end condition at the top. Then when I come to the end condition at the bottom, I'll be looking at condition number 2, in which case when I go to the column for the end condition at the bottom, I'll have to read along the what? The column number 2. Now reading along column number 1 for end condition at the top and column number 2 for end condition at the bottom gives me a beta value of what? 1.3. Now again, if we come back to our floor, if we come back to our ground floor, the distance from the surface of the ground floor slab to the surface of our first floor slab, as we saw whilst we were looking through the section of our building, was also equals to what? 3,000. Now, given that our beam has a depth of what? 400, it means that our clear space between restraints is equals to what? 2,600. Now, moving forward, to calculate for our effective height, we multiply our LO value, which is our clear height between restraints, by our beta value. And we've just identified our beta value to have what? To have a value of what? 1.30. So then our effective height between restraints is going to be equals to 1.3 multiplied by 2,600, and that gives us a value of 3,380 millimeters. Again, since we are doing a design for a short braced column, our LEX over H should be less than or equals to 10. By inequality, our H value should be greater than or equals to LEX over 10, where our LEX value is 3,380. Now dividing it by 10 gives us an H value of what? 338, which can be approximated to 350 millimeters. Now moving forward to the Y direction, our LEY over B should also be less than 10, less than or equal to 10, since we are doing a short unbraced column design. Also by inequality, our B value should be greater than or equal to LEY over 10, which gives us what? 3,380 divided by 10, which ultimately gives us a B value of 338. That can also be approximated to what? 350 millimeters. Meaning that when we come to our ground floor level, our column is going to have a dimension of what? 350 what? By 350. So then by this method, we've been able to identify the dimensions of our column for the first floor level, which is 320 by 320, and when we come to the ground floor level, we're able to identify it to be what? 350 by 350. Now, having identified the dimensions of our column, we now move ahead to do our load estimation. Now, in doing our load estimation, we realize that there are series of columns within our structure. And now these series of columns are supposed to help carry all the loads that the structure would have to carry. So then each column has a given amount of load it's supposed to carry. So we now move ahead and determine how much load our column is supposed to carry. And that one is determined, or that one is arrived at by determining the equivalent area of the slab or the equivalent area of the building that our column is supposed to resist. If we take our column, located at our intersection C, at the intersection between the grade line C and grade line 7, it has 4 different panels to its side. To the left side, it has a dimension of 1,600. To the right side, it has a dimension of 1,600. Then to the upper side, it has a dimension of 1,800, and to the lower side, another dimension of what? 4,350. Now, if it comes to the area of the floor slab that the column is supposed to carry, then when we look to the side, which is the grade line, which is the part of the slab bounded by the grade line D and C, the column on grade line 7C is supposed to carry half of the beams and the slabs in that direction. So then the equivalent area of floor slab that is supposed to be resisted, or that is supposed to be supported by our column, is what is being marked by the red line. or by what is being marked red on our floor slab. So that if we take between grade lines C and D, our column is supposed to carry half of the elements within that section. If we take between grade line A and C, our column is supposed to carry half of the elements within that section. So then it will carry half of the beams in that section, half of the slabs in that section, half of the roof in that section. Everything within that section would have to be resisted by our column C7. If we count between grade lines 6 and 7, again our column would also have to resist what? Half of the element, or would have to support half of the element within that section. And similarly to between grade lines 7 and 8, it would also have to resist what? Half of the elements, or have to support half of the elements within that grade line. So then moving back to grade lines C, D, C, and A, you would realize that the equivalent area that the column would have to carry between grade lines C and D is equivalent to what? 800 millimeters. So out of the 1600 millimeter distance between our grade lines C and D, our column would have to support 800 millimeters of that span in between the two grade lines. Now between grade lines C and A, with a span of 3600, our grade line C7 would have to carry a span of 1800, which is half of the distance between C and A. Similarly, if we come to the horizontal, when it comes to the vertical, between grade lines 6 and 7, the span is 1800, and our grade line C7 is supposed to carry half of that span, which would be equals to what? 900. Then between grade line 7 and 8, which has a span of 4300, our column on what? Grade line C7 would also have to carry about half of that value. Now putting everything together will give us the equivalent area of our building that our column C7 would have to what? Support. So then our equivalent area of support is given by half of grade line DC plus half of grade line AB multiplied by half of grade line 6-7 and grade line 6-7 and 7-8 added together. So we have 800 plus 1800 multiplied by 900 plus 2175. This gives us an area of 2.6 multiplied by 3.07, which translates into a total area of what? 8.0 meters squared. So then for the total floor slab within our building, our column C7 is supposed to support an area of what? 8.0 meters squared. Now, having identified the area of the floor slab or the area of our structure that our column is supposed to support, we move ahead and do our load estimation. Now for our load estimation, again, we are going to estimate our loads for the two different levels within our building, i.e. for our first floor level and for our ground floor level. And for each of the two levels, we are going to estimate for our dead loads as well as what? As our live loads. So then for our dead loads, what would constitute it? Our dead load will be constituted by 1, the self-weight of the beam itself, the weight of the roof beam, and the weight of the roof, including all the roofing materials and everything that makes up the roof. Now, in determining the self-weight of our column, we'll go by the methods that we employed during our slab design and our beam design, where we'll pick the density for our concrete made out of natural aggregate with a value of 2307 kilograms per meter squared. Then whatever value that we pick, would multiply it by the volume and the acceleration due to gravity. Now for our density, as we picked from our Bscode, it was 2307 multiplied by the volume of our column, which is equal to the cross-sectional dimension that we calculated for and had as 0.32 by 0.32 by the total length of the column, which is 3 meters, multiplied by our acceleration due to gravity, which is 9.8, giving us a total weight of our column of 6.95 kilonewtons. So then for the self-weight of our column, it has a value of 6.95 kilonewtons. A similar approach is adopted in calculating for the roof beam, and once that is done, we realize that the self-weight of our roof beam is equals to 40.74 kilonewtons. Then the element that I will use for our roof load within the area which is being supported by our column is also estimated for, and that gives us a value of what? 10 kilonewtons. Now adding all our dead loads together gives us a total dead load of what? 31.69 kilonewtons. Now, having finished with estimating our dead loads, we now move ahead and estimate for our live loads. For our imposed loads, as we've been using for the other elements, we had an imposed load of 1.58 kilonewtons per meter squared. As in, for every meter square of space that we took, it had an imposed load of 1.5 kilonewtons. So that if our floor or if our column is supporting an area of 8 meters squared, then what would be the imposed load value for that 8 meters squared? So we pick that 1.5 kilonewton value and we multiply it by the area being supported by the floor slab, being supported by our column. And multiplying the 1.5 by 8 gives us a value of what? 12.0 kilonewtons. So having arrived at our total dead load and our imposed load, we can now move ahead and determine our design load for our first floor level. Bear in mind, this is the design load for only our first floor level. So then for our design load, we have it being equals to 1.4 GK plus 1.6 QK. That goes on to translate into 1.4 multiplied by 31.69, which is our dead load, and 1.6 multiplied by 12, which is our live load. This gives us 44.37 for our dead load, or for our design dead load, and 19.2 for our design live load. Adding everything together gives us a design load of 63.57 kilonewtons. So then for our column at the first floor level, it's supposed to resist an axial load of 63.57 kilonewtons. Now, having finished with this one, we now move on to the ground floor level and estimate for the load that the ground floor level column would also have to resist. Again, we'll look at our dead loads. Now, for our dead loads, we'll consider the self-weight of the beam, the self-weight of the column, the first floor beam weight, the slab weight from the first floor, and the weight as coming from the first floor column. Now, when it comes to the self-weight for the first floor, for the ground floor beam, it goes through the same principle as we did for the first floor column, in which case we pick our density for our natural aggregate concrete, which is 2307 kilograms per meter squared. Then we multiply it by the volume of the first floor column as against the acceleration due to gravity. So then we have our density value being equals to 2307. So in determining the self-weight of our ground floor column, we do it in much the same way as we did for the self-weight of our first floor column, in which case we take the density for our natural aggregate concrete and we multiply it against the volume of our first floor column and the acceleration due to gravity. Our density value, as we realize, is equals to 2307 multiplied by the volume of our first floor column, of our ground floor column, which is 0.35 multiplied by 0.35 multiplied by 3. Since we had our cross-sectional area for our ground floor column being equals to what? 350 by 350, then multiply everything by 9.8, which is acceleration due to gravity. This gives us a floor column weight of 8.308. So then for the self-weight of our floor column, it's equals to 8.308. Now, applying the same principles to the first floor beam, we determine our first floor beam weight, which is equals to 13.38, our slab weight, which is equals to 60.42 kilonewton, and the weight from the first floor column, as we realized from the total dead load from our first floor, which was equals to 31.69. Now, adding all of these together gives us a total dead load of 133.8 kilonewtons. Now, moving on, we now come and calculate for our imposed loads, and we add the imposed loads from our roof level and from our first floor and from our ground floor. In which case, from our roof level coming onto our from our ground floor, we have it. Now, having finished with our dead load, we now move on to estimates for our live load. And for our live load, basically, we are looking at our live load coming from the roof level onto the first floor, and from the first floor coming downward. From our first floor coming downwards, we have a live load value of 12.0 kilonewtons as we calculated before. Then for the roof also, we had it to be in equals what 12.0 kilonewtons. Now adding everything together gives us a total dead load of what 24 kilonewtons. Now having been able to estimate for our dead loads and our imposed loads value, we can now move ahead and calculate for our design load value for our ground floor level. Now for our ground floor level, our design load becomes what 1.4 multiplied by our dead load plus 1.6 by our live load, which gives us 1.4 multiplied by 113.8 plus 1.6 multiplied by 24. This gives us a value of 159.32 plus 38.4, which ultimately translates into 197.72 kilonewtons as being the ultimate design load for our ground floor columns. Now, having arrived at the values for our ultimate design loads, we now move to do our axial load and moment analysis. Now, if we go to the section 384 of our Bscode, which talks about the normal eccentricity of short columns resisting moment and axial force, it says that a short column usually needs to be designed for the maximum design moment about one critical axis. But where, due to the nature of the structure, a column cannot be subject to significant moment, it may be designed so that the ultimate load does not exceed the value given in, or the value given by our equation 38. Now, considering our structure that we are designing for, the amount of load on the column is not too significant, and neither is the loading too eccentric that it will cause too much moment in our section. So then, instead of doing a moment analysis on our section, since we have our moment, or since from our loading, we consider that our moment values are going to be very, very minimal. We are going to design our axial load, or we are going to design, since we have the moment in our section not being so much, we are going to design our column in such that the design ultimate axial load does not go beyond whatever has been given to us in the Bscode. So then we pick our formula as given by table 3 as given by equation 38, and we make sure that the axial loads, it goes on to say that where, due to the nature of the structure, a column cannot be subjected to significant moment, it may be designed so that the design ultimate axial load does not exceed the value of n given by the formula quoted as equation 38. Now, because the loadings in our structure isn't so much, and because our column is not so eccentrically loaded, it can be deduced that the moments that will be induced in the column wouldn't be that much, which would necessitate us designing for a moment in a particular plane. Now, if our moments are not so much as to necessitate us designing for the moment in a particular plane, then we can design it such that our ultimate axial load does not exceed the value of n as given in the equation. Now, with that one being said, then it means that we can pick this equation and make use. It says that where, due to the nature of a structure, a column cannot be subjected to significant moment, it may be designed so that the design ultimate axial load does not exceed the value of n given by the equation 38. Now, the value of n given by the equation 38 is the axial load capacity of our column, which is the maximum amount of axial load that our column can resist. Where we have our structure not being exerted on, or where we have it not resisting so much of moment, the code says that we should design our column such that the ultimate axial load that the column is supposed to carry does not exceed its column capacity. Now, considering the structure that we are designing for, our loadings are not that much, and again, our column is not so eccentrically loaded, which will cause a large amount of moment within our column, in which case we can design our column in such a way that the ultimate axial load would not exceed the axial load capacity of our column. So then we are going to design our column such that the load in it does not exceed the amount of load that our column should be able to resist. Now, if we take the equation 38, the variables being given in the equation 38 are n, which stands for the axial load capacity of our column. We take the FCU, which is the grade of our concrete. The AC is the net area of concrete within our column. Our AC is the net area of concrete within our column, in which case our AC can be said to be equals to A minus ASC, where our A is the gross So that if we take the terms of our equation 38, the N stands for the axial load capacity of our column, the FCU stands for our grade of concrete, the AC stands for the net cross-sectional area of the concrete, the ASC stands for the area of steel reinforcement, and the FY our grade of concrete. Now our AC, as said, is the net area of concrete, in which case we can say our AC is equals to A minus ASC, where the A is the gross cross-sectional area of our column. Now if we are taking our AC as being equals to A minus ASC, then it means that our axial load capacity of the column can now be rewritten as M being equals to 0.4 FCU into bracket A minus ASC plus 0.8 FY ASC. Now, if we're able to rewrite our axial load capacity equation in this form, then we can solve this equation and make our ASC the subject, in which case we can use that equation to determine the amount of reinforcement required to resist the axial load that our column is supposed to carry, assuming we equate our N, which is our axial load capacity, to the amount of load that the column is supposed to carry. So that if we equate our N, or the load capacity, so that if we equate our design load to our N, which is supposed to be our load capacity, and we make the ASC, which is our area of steel reinforcement, the subject, we should be able to calculate for the area of steel reinforcement required to carry as much load as our column is supposed to carry. Now, making our area of steel the subject of the equation yields us with this formula to calculate for the area of reinforcement required for our concrete section, whereby our ASC is equals to our N, which is our axial load capacity, which is now being equated to our design ultimate load, minus 0.4 FCU multiplied by the gross cross-sectional area of the column, everything divided by 0.8 FY less 0.4 FCU. Now, applying this formula to both our column at the first floor level and the column at our second floor level would yield us the information we have in the chart. If we take the various building level from the ground floor level, now applying this formula to our various columns, that is the column for the first floor level and the ground floor level, would yield us the information that we have in the chart. For our first floor level, we had our design load to be equals to 63.57 kilonewtons. Now, when we substitute the various parameters into the equation as we saw, to the various equations as we saw, in which case we had our area of steel being equals to N minus 0.4 FCU A minus 0.8 FY minus 0.4 FCU, Once we substitute the various parameters into the equation for our first floor, in which case our n now becomes 63.57. Our n now becomes 63.57. Since it's in kilonewtons, it's multiplied to the power 3 minus 0.4 multiplied by 30 multiplied by 320 by 320 to make up for the gross cross-sectional area of our column. Everything divided by 0.8 Fy minus 0.4, where our Fy equals 250. Minus 0.4 multiplied by 30. The area of reinforcement value that was arrived at equals to minus 6198.03. Now, the negative value for the calculated area of steel reinforcement required is indicative of the fact that our column is adequate to carry all the loadings on its own without steel reinforcement. That is how come our area of steel reinforcement required is giving us a negative value. Should it have given us a positive value, then whatever value that we got would have been the area of reinforcement we need to add to our concrete section to help it resist the load that is being applied on it. Now, once we have it being negative, it means that our concrete section is adequate on its own to carry the amount of reinforcement or to carry the load which is being imposed on it. Now, under such a condition, the ideal thing to do is to provide the minimum area of reinforcement for the concrete section. Where you have the concrete section being able to carry all the loads without the help of reinforcement, per the requirements of the Bscode, we are supposed to provide for it the minimum area of steel required. And according to the Bscode, for a rectangular section resisting compressive loads, the minimum area of steel reinforcement required is equal to 0.24% of the gross cross-sectional area. So that if I pick the gross cross-sectional area 100 AS, 100 AC, AS over BD, it should be less than or equal to 0.24%, meaning that our minimum area of reinforcement AS, our minimum area of reinforcement can be equated to 0.24 BD all over 100, in which case we have our area of reinforcement being equal to 0.24 multiplied by our B, which is 320, and our D value, which is 320. Which is 320. Everything being divided by 100. Now this gives us a value of 245 millimeters squared as the area of reinforcement that we are supposed to provide, as the minimum area of reinforcement that we can give to our steel section. Now moving forward, because we are providing a minimum area of reinforcement, the Bscode stipulates that for a rectangular column section, the minimum number of reinforcement that can be provided for that section should be 4. If I have a rectangular section, the minimum number of reinforcement that can be provided for the rectangular section is 4. In the case of a circular section, the minimum number of reinforcement that can be provided for such a section is equals to 6. Now, because we are dealing with a square section which falls within the remit or periphery of a rectangle, it means they are supposed to provide a minimum of 4 diameter bars. So then we move ahead and provide 4 number 16 mm diameter bars, which will give us an area of reinforcement of how much? 804 millimeter squared. So that even though we are providing a minimum area of steel reinforcement required, because we are using 4 16 mm diameter bars, the area of reinforcement that we are provided into the section now becomes what? 804 millimeter squared. Now, having finished with that one, we move on to the ground floor level. Now, at our ground floor level, we had our design load to be equals to 197.72 kilonewtons. Substituting all the parameters into the equation, just as we did for the first floor slab, gave us a calculated area of steel required as being 6767.45, also with a negative sign to it, indicating that at our ground floor level also, our concrete alone is strong enough to resist all the axial loads in compression without the help of reinforcing steel. Again, for the remit of reinforced concrete design, we cannot put our concrete section into service without reinforcement, and so we are supposed to make provisions for the minimum area of steel reinforcement for the section. So as we did for the first floor level, we move ahead and calculate for the minimum area of reinforcement required for our concrete column section at the ground floor level, and the minimum area of reinforcement required at that point was given as, or was found to have a value of 294, going through the same processes as we did for the first floor level, in which case we had our AS 100 AS over BD less than or equals to 0.24. Then we equated our AS to 0.2 for BD over 100. This time, let's not forget that our BD value for our ground floor column is not going to be 320 as we had for the first floor. Since when we come to our ground floor level, our column dimensions are 350 and 350. Hence, the minimum area of steel reinforcement required being equals to what? 294 millimeter squared. Then the area of steel reinforcement provided was what? 804, which is equivalent to what? 4 number 16 mm diameter bars. Now, having finished with our axial loads analysis, we now move on and check for shear in our column. Now, this is the provision of the Bscode for shear in our column. It says that the design shear strength of column may be checked in accordance with section 34512. That was the section that we used in checking our shear reinforcement for our concrete beams. It now moves on to say that for rectangular sections in compression, no check is required. For rectangular sections in compression, no check is required, provided MN does not exceed 0.6 H and V does not exceed the maximum value given in 34512. And the maximum value given in the 34512 was the 0.8 root of FCU, or the 5 newtons per millimeter squared, whichever be the lesser. Now, if we have our shear stress not exceeding any of these values, then it says that for a rectangular section in compression, no check is required. And again, since we're not designing for moments whereby we could compare our moment value and our axial force value, for the column that we design for, we need not do a rigorous shear design. We only need to provide the minimum area of steel reinforcement required for our shear reinforcement, just as we saw under the beam design, where we provided minimum lengths for the full length of the beam. And at this section also, we are supposed to go and provide minimum lengths for the full section of our columns, just as we did under the beam. Now, moving forward, when it comes to the deflection of columns, it says that no check is necessary under the following condition. 1. For a braced column, within the recommended limits of slenderness, no specific check is necessary. Within the recommended limits of slenderness, no specific check is necessary. Now, because we are not dealing with a braced column, we can't really rely on the first provision that is given. So we move on to the next provision, and it says that for an unbraced column, no check is normally necessary if in the direction and at the level considered, the average value of LE over H for all the columns is not more than 30. No check is normally necessary if in the direction and at the level considered, the average value of our effective length over the height of column for all the columns is not more than 30. Now, if we go back and we look at our effective height, now if we go back to our initial dimension, once we know our initial dimension, we constantly make sure that our effective height, so our effective length over the height of the column were not more than 10 in both the first floor level and the ground floor level, under which case our LE over H is nowhere near the 30 level being given. So then we don't need to go in and do a rigorous check for deflection for our columns. So once we have our LE over H value being less than 30, it means that we can opt out of doing a deflection check for our columns. And so at this point, we can fully say that we've fully gone through our column design, our shear is okay, and our deflection is also okay. In which case, we can now move ahead and sketch the section of our concrete column. And the section of our concrete column has been sketched for us with the reinforcement what provided in it. Now, having come this far, we can now say that we fully finished designing our reinforced concrete column, and our sketches and our drawings are ready to be sent to site for construction. That brings us to the end of our